Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about, science and math. Today we're in chemistry class talking about the periodic table and bonding. So this is Unit 4, and we start off with a literacy connection. Okay, so I'm going to read you a story. Now, so you have to pay close attention so you understand what this has to do with chemistry. So this is out of print. It's a great book. It is People in My Family. Okay, y'all ready? Okay. Oh, I have 5 people in my family. And there's not a one of them I'd swap. They're going to the park, it looks like. There is a sister and 2 brothers and a mother and a pop. That's me. 5 is such a lovely number. I'm awfully glad I've got 5 people in my family. 1, 2, 3, 4, 5. Now there's a little foreshadowing here that we have a coming conflict. Wouldn't be a story without a conflict, right? See, I told you there was a literacy connection. Well, I've got 5 monsters in my family, and we all have lots of fun. Furry wife and scary husband, fuzzy daughters, hairy son. 5 is such a scary number. Oh, I'm so glad I have 5 monsters in my family. 1, 2, 3, 4, 5. This is the climax. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. They're seeing each other. Now this is the denouement. Remember that? 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. They're all happy together. And then there's questions if you're like at 5, but you're not. So this is our part. What could this have to do with chemistry? Okay, so before we get there, let's talk about this. Okay, how do you know that this is a family and this is a family? How can you tell? Yes, Divine. They look similar, okay? So they have similar characteristics. What are some similar characteristics of the monsters? Yes.
They're furry.
They're furry. They're all got a lot of hair. What else is similar about them? Yes.
They're colorful.
Well, they're kind of colorful too.
Yeah.
So what else?
Oh,
Yes.
they have the same features. Like, for example, the monster ones, like all have the same type of eyes. And
Eyes. They all have kind of googly, scary eyes, right? So the eyes are similar. What else do you see similar about the monsters?
Their shapes.
Their shapes, like their mouths. If you look at their mouths, they're similar. Do you see that? Okay, now what about the Muppets? How are they similar? How can you tell they're a family?
Their noses.
Their noses, except like he doesn't have a nose, but their noses are at least alike. So some of them have more similar features. That's good. Okay, now this is the next thing. The families are alike, but they also have representative members that have something in common, right? For example, the dads. How can you tell by looking which Muppets are the dads as opposed to the other members? Yes, Divine.
they're usually like the tallest ones.
They're like the biggest. Anything else that the dads have in common?
They wear something differentiating. For example, the monster has a bow tie on.
But the dad doesn't. So what's something that they have the same? Something more similar about them.
His hair, like on the other side, balding.
And he's sort of balding looking too, isn't he? Little flatter on top than the other monsters. They both have the biggest noses of the family. Also, like maybe the eyebrows. They have the most eyebrows of their family. Do you see that? Each family has a smallest member, and they both happen to be pink, so they have something in common. So what about the moms? How do you tell which ones are the moms? Yes.
They're both gingers.
They both have red, sort of curly hair. So they both have something similar there. They both have ginger hair. Okay, and so do you see this? Okay, so now what in the world does this have to do with chemistry? Any guess? Yes, Dwayne.
Families in the periodic table, maybe like you
Family and period. You're on the right track. Families in the periodic table. What?
like they have similar characteristics that help them be created.
They have similar characteristics and similar.
Property?
No.
Water? No.
Or
Oh.
Similar characteristics.
they have similar members. So now then, so families have something in common with their family, but they also have things that are in common. They sort of have representative members, right? So which is more though? Which is stronger? Is this father more like the other Muppets, or is he more like the other father? Which do you think? The other Muppets. You got the right answer. So in chemistry, families have the similar properties. They also have similar members, but they have more in common with their family than their row. Does that make sense? Than their period. All right, yay. I think you learned what you need to know from this. All right, so look at your notes, and you'll see Mama Muppet on there. Okay, so let's start talking about the notes. Very good. All right. People in my family. See, we started off with our great book. People in my family. So columns or families are more like each other than periods, rows that have similar members. So the rows have similar members, but the families are more alike. Okay, so let me show you that a little bit. On the periodic table, you have the columns going up and down. Those are the families. So like this family is the alkaline metals. They are alike. They all react the same. They're all highly reactive. They both react with water. They're all alike. But also, these are the noble gases. They're all alike. They don't react with things. They're very inert. But still, there's some similarities in the members. There is a similarity in hydrogen and helium. They're both so small, they're gases. Do you see that? They both fill the s orbital, the 1s orbital. That's the similarity. So as you go down the column here, francium, cesium, or let's look at this one. If you look at this family as you go down, at the very bottom, it's so big, it's radioactive. So these down here are so big, they're radioactive. Noble gases, if you go down so far, is it radioactive? Is radon radioactive? Yes. So these are so big, so they have a similarity, but they're still more like their family. Is that good? That makes sense to you? Okay, next idea. Okay, so the next thing is, what do elements want? They all have a goal. There's someone they want to be like. Anybody know? In England, what do they want to be like? The king, the queen, right? So they all want to feel like a noble gas. Hey, this is not good. This is not going well. It's already going wrong. So this is the rule. For our noble gases, when we learned about their electron configuration, they all had 8 electrons in their valence level. That's what makes them feel stable. So they all want to be like a noble gas. They want to follow the octet rule. The octet rule. So they all want 8 valence electrons. Okay. So, so the guy who figured this out, he said he figured out that all the elements seem to want to have 8 electrons. And so he called it the octet rule. And he thought, there are patterns in creation that go beyond logical explanation. For example, the spiral of a snail shell is a very complex mathematical thing. If you've ever, y'all probably haven't, some of y'all might have done honors algebra 2 by now. Did you do the complex math of a spiral? Did you learn about that when you did conic? Y'all probably won't do it till pre-calculus. Anyway, so there is very complex math with spirals. And that complex math is found on the lowly snail and in a galaxy. So there is this pattern of mathematical complexity. It's in a hurricane. It's in a tornado. It's in a fern frond unrolling. There's this very complex mathematical pattern. Okay, and it is found throughout creation, from the snail to the tornado to the galaxy. So does a snail and a tornado and a galaxy have much in common? Nope. But they all have this incredibly complex mathematical thing applied to them. Okay, you following so far? So this guy said, when he figured this out, he said that seems to be a pattern here, a complex mathematical pattern based on the number 8, just like there is in music. So music, the scale has 8 notes, and the atoms seem to all want 8 electrons. So he published it, and they all laughed at him, said he was stupid and wrong. He died, and then they went, whoops, he was right. So he never found out in his lifetime, but the guy who figured this out was right. There are 8 notes in the musical scale, and there is a mathematics to music. You understand that, right? If not, you'll learn that in physics class. All about the nodes and the frequency and the wavelength. Music is physics. And yes, there's all this math that you can do with it. And some of y'all might have learned some of that in music theory. Well, that same math, there is a math in the elements based on the number 8. Did you sort of follow that flow? But poor guy, never found out he was right. Okay, so this thing that all the elements want something, they want to have an octet, and it all has to do with energy and stability. So because of that, it causes something called periodic trends. Now, I think the easiest way to remember this is how to remember what everything wants on the periodic table is to think of the electrons like children. Much easier than just flat trying to memorize it. If you flat try to memorize it, you'll get it wrong on the test. You'll forget it. Okay, so first of all, we have the alkaline metals and the alkaline earth metals, the ones that's column 1 and 2 on the periodic table. Okay, everybody thinking about them. Okay, so when they do their electron configuration, they are just like the noble gas before them, except one extra electron. All of these end with something in a s orbital, one electron in an s orbital. Does everybody see that? If they could lose that electron, da-ding, they would feel like a noble gas. This column, they all end with S2, 2 electrons in an s orbital. If they could lose 2, da-ding, they would feel like a noble gas. Do you follow that? So what do they want to do? They want to lose electrons. Can you follow that? Okay, so these want to lose electrons. Okay, so I say these are like those bad parents who abandon their children and leave them at Walmart. This used to happen all the time. People would be shopping at Walmart, looking on the shelf, and boom, there's the baby there. People would just leave a baby at Walmart, and because they don't want that baby. They want to get rid of it. Well, now they've made laws where they like have a box even, I think, at the fire station. And if you want to leave your baby there, you can just leave it there and you will not get arrested. They will take because otherwise people put them in dumpsters and they die. But if they put them in the baby box at the fire station, the baby at least gets to live and be adopted, okay? So these are the terrible parents who want to leave their baby at the fire station. This group wants to leave one baby at the fire station. How many does this want to leave? Two babies at the fire station. Everybody got it? You're going to remember this now, right? Okay. Bad parents, okay? Now, the ones over here, like the halogens, if they could just have one more electron, they would feel like a noble gas, okay? So these are the crazy ladies who dress up like nurses and go to the hospital and try to steal a baby. They're out there. There are ladies who want babies, and also people who just want to steal babies to sell them and stuff. Okay, so these are terrible. They want to steal one baby, and they will feel like a noble gas. Now, when my son Joshua was born, when you have a baby, because of this, and see, that's why the person who's dressed up like a nurse, I thought I had on here. Anyway, so when my son Joshua was born, that I had him at Caldwell Star, and they explained to me how they had technology so nobody could just come in and steal your baby. There's like baby LoJack, and they put this little monitor on the baby that if the baby is taken through the doors out of the maternity section, then the hospital goes into lockdown. All the doors lock, everything locks, so they can't get out with the baby. Okay, so there's baby LoJack. Well, my youngest son, Joshua, when he was 10 days old, he got RSV. It's a respiratory virus, kind of like coronavirus, but he got this respiratory virus and he almost died. So he was at Scottish Rite. And while we were at Scottish Rite, he was in the respiratory virus wing, and so this nurse came in, and I'm there with him, and I said, having just had him at the hospital, I was like, well, what kind of security do you have? So nobody, does he have the baby LoJack on him that everything shuts down, someone tries to steal him? And it was this old nurse, and she laughed, and she said, honey, nobody wants your baby. He's sick. They don't try to steal these babies. And I was like, I want him. But anyway, there's no security. Nobody wants the kids at Scottish Rite. They're sick.
That's what my doctor thought.
Really?
When I was born, my doctor purposely went on vacation so he wouldn't be there. I had to be in the hospital for a week because the doctors that helped deliver me did not know it was coming out with one hand. And then he arrived back to the hospital that same week and avoided the crap out of my mom.
That's just evil. Just evil. So wrong. So wrong. Oh, makes me angry to think about it.
My mom thought I died because I didn't come out screaming, and they told my mom, I don't know how to tell you this. And I wasn't screaming, so she fucking died.
Oh.
And then I started screaming, and she just went all demonic, like, gave me a bunch of hours.
Oh, yay. So anyway, so the ones near the noble gases, like the halogen, they want to gain electrons. They want to gain electrons. Now, so these want to gain one electron. How many does oxygen's family want to gain? How many does nitrogen's family want to gain? 3. So now, how many would carbon's family want to gain? 4, but notice carbon is also 4, 1, 2, 3, 4 from the other side. It's right in the middle. So really, carbon's family is too far away to gain or lose electrons. They can, but it's real extreme lab conditions that can cause this. So what they do instead is these are a parent situation that some of you in this room have. You've never been stolen, you've never been abandoned, but there are some of you in this room who has this new parent situation. Anybody can guess what it is? Yes, this is the divorced parents, okay? So our nonmetals, they're too far from the edges to gain or lose electrons. So instead they share. Most of you who have divorced parents, you have a custody arrangement where you go to mom some and you go to dad some, right? So, and it's a sharing arrangement. Now, most of you, the sharing is not equal. Usually mom gets you more, sometimes it's dad, but it's not usually on Monday you're with mom, Tuesday with dad, Wednesday with mom, Thursday with dad. I have known one student who had that. Her mom bought a house next door to her dad so they could do this. Are you the Monday, Tuesday?
I'm at my dad's Monday, Tuesday, my mom's Wednesday, Thursday, and they alternate Friday, Saturday, and Sundays. Because, like, the way it worked out is really weird. My stepmom works with my stepdad's sister, and they're, like, best friends. So my stepdad's family goes over to my dad's house for holidays, and, like, everyone's besties. So it's,
That's how it was the other one. And I've had other students go, when I've told them about this one where they bought houses next door to each other in the same neighborhood, they were like, that would never work. But for some it does. Yes, Nicholas?
I'm really confused because I don't ever really get to see my dad, so like,
How would that work?
I don't know.
I don't know. Well, so let's talk about how this applies to the how it applies to the situation. We'll talk about yours too. Okay. All right. So with most elements that share an electron, it's unequal, and one of the atoms gets the electron more than the other one. It's an unequal arrangement, and that causes partial negative and partial positive charges. Now, there are situations where they share exactly equal, like in her situation. And what it is that means the two elements are exactly the same. So oxygen will bond to oxygen. They will share their electrons exactly equally because the two oxygens have the same strength to hold the electron to itself. But if you have oxygen and hydrogen, oxygen is much better at holding an electron than hydrogen. So oxygen just about always has the electron. Hydrogen very rarely gets it. So I think that would be more like your situation where you don't see your dad much at all. That would be the bond between oxygen and hydrogen because oxygen is just a bully and keeps that electron all the time. Okay, so are we following the chemistry of it? Okay, so nonmetals. These are nonmetals, not metals. Nonmetals work out sharing agreements. Sharing arrangements, okay? Now, what about the metals? What about these metals in the middle? Oh, let me show you one other thing too. Okay, so this family loses 1 and becomes +1. This family loses 2 and becomes +2. This family loses 3 and becomes +3. So boron's family actually loses 3 and becomes +3. Carbon's family we just skip because it works out the sharing arrangements instead. Nitrogen will steal 3 and become -3, oxygen -2, the halogens -1. So it's a pattern. It's 1, 2, 3, skip, -3, -1, -2, -1, zip. Zip because the noble gases do nothing. So I have this written on my periodic table. Remember your periodic table cheat sheet that you write on? You need to write this. +1, +2, +3, skip, -3, -2, -1, zip. So write that on your periodic table to add to your cheat sheet. It will be very useful on test day. Okay, so the next idea, what about those metals, those transition metals in the D block, including tin and lead, all of those metals that aren't in the alkali, the first two columns, the base columns, okay? So what I say about them is they are hippies. See my peace sign? They're hippies. And let their electrons run, what I write here, wild and free. Okay, so let me explain to you about the hippies. Yeah, especially in the 70s, there were hippies, and they would live in hippie communes, okay? And in these hippie communes, there were no rules. There were no marriages, we'll say. Anybody could be with anybody they want, okay? Wild and free. Long hair, bare feet, music, drugs. Okay? Now, they had kids. And the kids would often call all the women in the compound mom and all the men dad. And then the kids would just run around and do whatever they wanted. Dirty little barefoot kids with long hair. Okay, you can see that, you can imagine the situation. Okay, and this was considered great. This was idealized. You heard it a lot in the music of the time. There's a song called "In Seattle." Seattle had a lot of hippies. A lot were on the West Coast, and there's a line that says, "Growing up like a child, beautiful, free, and wild." So it was just this. They felt like it was terrible to grow up with structure and rules. That people should be free. You even hear it a little bit in the lyrics to the song "Born Free." But there were all these songs. All this. That this was great. This was the way to do it. That you needed to let children grow up in complete freedom and wild and in nature and eating granola, and this is the way to raise kids. Okay, so they would just run around wild and free. Now, anybody know what put a stop to this? Any guess? It sort of all stopped one day. Yes.
CIA.
What?
The CIA, they're all.
No, not them. They didn't care what the hippies were doing. Wasn't them. Yes?
CPS.
No. Do you have a guess?
AIDS.
You would think, but it was gone before AIDS. AIDS hit in the 80s. It ended before that, yes?
The police.
No?
Dad hears.
Y'all don't know. I've had people guess it before. Divine?
Oh, okay.
You weren't ready. Olivia?
Okay, so I remember seeing a movie about, and like all the hippies just like got on a bus and went somewhere.
Okay, this is why. Have you heard of Charles Manson
Oh.
and the Manson murders? Yes. Okay, so they were one of those hippie communes. And everybody thought they were great. Charlie Manson hung out with the Beach Boys. He was hanging out with all the top music acts of the day. They were friends with all of that. It was all part of the California hippie thing going on. But Charles Manson was crazy and evil. And he wanted to start a race war so that then, like, the hippies could take over the world, kind of thing. So he had his followers go kill a bunch of rich people, Sharon Tate and her friends, and she was pregnant at the time, and they tried to make it look like maybe it was racially motivated. Well, it really wasn't. It was just kind of crazy and evil. Well, then that horrified the nation. That these, peace-loving, free-loving hippies went on a murder rampage, and that kind of was the end of the hippie communes. That it all ended in a day when Charles Manson followers killed everybody at Sharon Tate's house.
So where did all the hippies go?
They went like home. They kind of paired up and got married and had more normal lives.
Dang.
Most of them ended up moving off the compound and settling down, giving up the hippie lifestyle. All right. So this is what what in the world does this have to do with chemistry? Okay, back in, but this is going to make you remember this forever and ever. Okay, so what these metals do that are in the middle is they make it where their electrons are not assigned to a particular nucleus. Just like how the hippies did not assign the children to a particular family, but the children could run free and wild, the electrons run free and wild, and they flow between the nuclei and can go from one to another uninhibited. That is why metals are good conductors of electricity and heat, why they're shiny. It's because they have free electrons. Does that make sense to you? So these metals in the middle, they're just free and loose with them. And it gives them their properties. Okay, so there are 4 ways of saying the same thing. I'm afraid to touch this and scroll. I'm going to try a scroll over here. If it doesn't work, I'll get it from last year, but we'll try it. We'll give it. What do I need to do?
I would not
Is that?
but I would go and be like, hey guys, what do you guys do? I want to document.
Oh, it scrolled. Okay, so the next part here is there are 4 ways of saying the same thing. But if you understand what I just explained to you about the families, it's not hard to understand. Okay, the first one is electronegativity. Electronegativity is the ability to attract electrons to oneself. If you're an atom, how close can you pull those electrons in? I already told you that oxygen is better at it than hydrogen. Now, thinking about what they have in mind, who do you think is going to be able to hold their electrons tighter? Lithium or fluorine? Which one do you think? Who's going to hold their electrons tighter? Fluorine. Lithium doesn't want to hold its electron tight. It wants to lose it. It's not even trying. It's like doing an arm wrestling with somebody who's not even trying. Where fluorine wants all of its electrons and to steal another one. So fluorine is more electronegative than lithium. Okay, now then, think about this though. Fluorine and iodine. Same column, same goal. One has 9 children, the other one has 53. Who do you think's going to be better at holding their electrons close? Fluorine or iodine? Fluorine. Why?
Because they
They have less. And remember, what makes the electrons stick to the nucleus is opposites attract. Nucleus is positive, electrons are negative, opposites attract. But if you got all the way down to iodine, then you've got electrons in between the nucleus and the electrons blocking. That's called, of course, we have to have special science names for all of this. It's called the shielding effect. And that means that the power of the nucleus for iodine is shielded somewhat because there's so many electrons. I always say that this is like me and my sister. I only had 3 kids. My sister had 6. And I was infertile for 5 years before I ever had the first kid. So I was really watchful of my children. When there was a rash of babies being stolen at that time. So if I went to the grocery store and my kid was in we call it the buggy in the South, or the shopping cart for people up north, I was holding on to if I was going to get something or look at prices or something, I would put my hand on my kid while I turned, because there was somebody who had just grabbed one out of a shopping cart recently at that time. So I just put my hand on him as I'm looking. Nobody was grabbing the baby. Now, do you think my sister could do that with 6 kids? No, absolutely not. Not only that, it's like if my kids were bad with just 3 of them, I was pretty good at being on top of it to discipline them. But with 6, like there would be one who's doing something bad, but if there was a couple of kids between her and that kid, he was getting away with it. Her son David, if you're seeing this, was a master at it. He always made sure if he was going to do something bad, there was at least 2 siblings between him and mom. He knew that she wasn't knocking 2 out of the way to go deal with him. I don't think he ever got spanked his whole life. He was smart, and he used the big family to his advantage. Y'all probably know some people like this who have big families. I have a cousin who had 7 kids. Same thing. 7. They were ones who got away with everything. Yes.
Family, and it's like every single family within our family has like at least 4 kids. Like we have 5 in our family, and then I have an aunt that has 7 or 8, and it's just like
It's a big.
like infinite cousins.
Have you seen that dynamic of the kid who makes sure they can get away with? Yeah. You know who I'm talking about. It's my nephew David. Love him to death. Love you to death, David, but he got away with everything. All right. So that is electronegativity. The next term is ionization energy. And this is the energy it takes to remove an electron. So this is like, how hard is it to steal an electron? Do you think which one do you think has a higher ionization energy? The energy needed to remove an electron. Do you think that would be fluorine or lithium? Which is going to take more energy to remove its electron? Fluorine, because it doesn't want to lose any of them. Lithium will pack the electron and gift wrap it for you. Fluorine is like, you're not taking my electron, because I need one more. Okay, the next one I already told you about. It's called the shielding effect. And it's the power of the nucleus is blocked by electrons. It's blocked by electrons. And then element size, okay? So this one is a little tough to get your brain around, but if you think about everything, you'll understand it. Okay, let's think about the first column here. As you go down this column, do you think the electrons get bigger or smaller? It's not a trick question. As you go down a column, do they get bigger or smaller? Bigger. Takes a lot more for francium's 87 than hydrogen's 1. Okay? But as you move across a period or a row, notice that this is going from 55 to 86. Do you think they get bigger or smaller? Smaller. Why? Why would it get smaller? It does. Why? Think about what they want. They want to hold on, as you go across, they want to hold on to their electrons more. Because as they get closer to noble gas, they're like, hey, I just need a little bit more and I'm going to be the noble gas. I'll be the queen bee. Okay, so here, they don't care about holding on to their electrons. They're big and loose. But as you go across, it gets smaller. Smaller as you go across. So element size, as you go across a period, the size decreases. And exclamation point, because that's a little surprising. So I need to draw for you. It's going to be a little difficult, but I'll do it. Okay, so do you have a little square over here on your notes? Did I draw that in? Nope. Okay, you're going to have to do it too. All right, so draw a little rectangle right here. This represents the periodic table. You can even label it, P table. Draw a little thing and call it the P table, okay? Now, so for number 1, for electronegativity, as it, we're going to color it, maybe I'm going to color it, I'm going to color it red. Okay. So for electronegativity, which is the ability to attract electrons to itself, for number 1, or just put number 1 here, as you go down, it decreases. And as you go across, do it like this, it increases. So, increase, and this is decrease. We'll say that D is decrease. A little D there. Put it over here. Decreases is D. All right, does that make sense? As you go down, it's less able to attract electrons. As you go across, it's more able to attract electrons. Good? Okay, so let's look at the next one. We'll make it green. Okay, so for ionization energy, the energy it takes to remove an electron. As you go down, do you think the energy it takes to remove an electron increases or decreases? Does it get easier or harder to take an electron away as you go down? Is it going to be easier to take my kid or my sister Gail's? It's going to be easier to take Gail's kid, right? We'd go to Walmart. She had kids. She's older than me. Her kids are older too. Her youngest of 6 is the age of my oldest. Okay, so I'd go to Walmart with her when her kids were little, and we'd hit the door, and they would just scatter throughout the store. Like, she wouldn't know where they were, and like you'd be shopping, and suddenly one of them would pop out of the the round thing where the clothes are. Suddenly a kid would be popping out of it. It'd be one of her kids. So would it be easy to steal one of her kids back then? No, they all got grown without getting stolen, but yes, it would have been much easier. Do you think I let my 3 hit the door of Walmart and scatter where they wanted to go? No, they had to stay with me. But I did not they were not free-range children. All right, so, and a lot of these ideas are back now. Okay, so as you go down, the energy it takes to remove an electron decreases again. And the energy it takes to remove an electron as you go across again increases. Do you see how this is all saying the same thing over and over again, just different ways? Okay, shielding effect. We'll make it purple. Purple, that's a nice purple. I guess that's pink. Let's try a better purple. That one, that's a good purple. Okay, so shielding effect. The power of the nucleus is blocked. As you go down a column, it does that shielding effect increase or decrease? Shielding effect, is it increased or decreased? What? Increased, yes. So as you go down, it increases. I'm putting I for increase. Okay, and as you go across, the shielding effect increase or decrease? Well, notice we have two things here. They're getting more electrons, but they're holding them tighter. Do you see that? So shielding effect as you go across is no change. No change. Those two things cancel each other out. Does that make sense to you? Can you follow that? Okay. All right, and our last one, element size. So what color should we make that one? We will make it, what's a good color? We'll make it orange. Element size, okay? So as you go down, do you think the elements get bigger or smaller? It's not a trick question. As you go down, do the elements get bigger or smaller? Bigger. So element size as you go down increases. But this is our trick one. As you go across, do they get bigger or smaller? Smaller. It decreases. Decreases. All right. This is a classic chemistry problems, is asking what these do. So all you've got to do now you understand the trends, all you've got to do is learn the vocabulary. Once you know the vocabulary, you will know this. This will be on your college chemistry test. This is a college chemistry concept where I tutor college kids too, and this trips them up, but it's not going to trip you up because you understand the trends now. I always have to read in my book. Let me get the book, and you'll understand it. All right, any questions about that? That's considered a hard part of chemistry. You feel all right with it? Good. Very good. Y'all are smart. Okay, so now what about bonds? Well, everything we've talked about so far has been individual atoms. What about bonds? Okay, so there are two kinds, and you probably learned these in your 8th grade physical science class. Did you learn about the bonds? Did you learn about the type of bonds? Yeah, I see some nods. Have you heard ionic and covalent before? Yes. Okay, so which one is transferred, ionic or covalent? No, it's ionic. Ionic is transferred electrons. How did I say it? Transfers. And covalent shares. This is our divorced parents. Shares electron. Compounds, atomic compounds like water have to be neutral. They have to be neutral. So that's why the math is like this. We're going to look at the charges, and if one element has a +1, the other one has a -1, then that would have a neutral charge. So our math is going to be really easy this time. Things like 1 - 1 = 0. Even you math haters can get behind this one, right? This one's going to be easy. Okay, so these are our sharing ones. Our transfer ones are the ones like the nurse trying to steal them. Okay, so first of all, we're going to learn about ionic. This is the transferred electrons. So what do opposites do? Opposites attract. That's right. That's why we got love here. Opposites attract. Now, do you remember, I already taught you cation and anion. Which one is positive? Cation, because cats are wonderful, positive, sweet little furry creatures. Okay? And the cations are on the left side of the periodic table. They are metals. The reason why is because these guys want to lose electrons. Electrons are negative. When they lose an electron, the atom becomes positive. Do you follow that? This is confusing to some people, that when it loses an electron, it becomes positive. Are you okay with that? Okay. So then anions are positive or negative? Negative. And so we can remember that cats are wonderful and positive, and mean old fire ants are negative. We all agree we hate fire ants. I told y'all last year I had fire ants building a nest in my room, a hill. They were coming in from outside and just decided to make a nice little fire ant hill right there inside the door. It was over there in what's Miss Foster's room now. I might should warn her. Watch out for fire ants. They'll come in the door. All right, so here's our example. Let me see if I did this yet. No, okay. So lithium wants to lose one electron. When it does, what charge is it going to get? What's it going to be? Lithium will become +1. And so remember how in science and math we're cool, and we're so cool we don't like to write all the ones. We like some ones to be understood. Do you remember in math where you learned about the understood one? When you learned about if it just says X, that it's understood that it's 1X. Everybody remember that? Well, we have a lot of understood ones in chemistry too, because we want to be just as cool as math. And if they're not going to write the one, we're not going to write the one. So what we do here is we just put a plus. I'm going to change this to a brighter color. I think y'all can see it better. Okay, so lithium, it would be +1, but you just do a plus. Now, you learned this already when we did our PhET computer interactive thing. You learned that the charge goes right there at the upper right like a exponent. Good? Everybody remember that from when we did that? Okay, I'm going to try to scroll. Everybody wish me luck. We can do it. We can do it. Go, scroll. It's very exciting. All right. Okay, so what would magnesium become? Everybody look at your periodic table. What do you think the charge of magnesium is going to be? Y'all know. What is it? +2. Notice how it's in the column where I told you to write in your periodic table +2. +1, +2, +3, skip, -3, -2, -1, zip. One day I just had a total brain freeze and I couldn't remember zip. And I was going, what is it? It's something that rhymes. Dip? No, that doesn't make sense. So anyway, it is zip. So Mg, you write it +2. Okay? What will aluminum be? +3, yes, good job. What would fluorine be?
-1.
Do we write the 1? No, we're cool. Just put a little minus there. Sometimes they'll write the -1, because sometimes the little negative is so small you don't see it. What will sulfur become?
-2.
Yes. Y'all are brilliant. Okay, let's try scroll again. We're having such a good scroll day. I complained about this to the Board of Education yesterday. I want action. But now it's doing better. It hurt. I complained about it, so now it's trying to act right. Okay, what will nitrogen become? Nitrogen, oops, go back to draw it once. Okay. It's going to be -3. Okay, so there's a pattern. And the pattern is our thing. 1, 2, 3, skip. -3, -2, -1, zip. All right, now, how do they get together and form compounds? Do we want to do that here? Well, first of all, you have to know, Lewis structures help with this. Do y'all remember how to do a Lewis structure? Let's do the Lewis structure of nitrogen. Okay, how do we do the Lewis structure? Do you remember? What do I count? I count how many over, right? Which will tell me the electrons. So nitrogen is 1, 2, 3, 4, 5. So I put 5 dots around it. You do one on each side before they double up. So that's the Lewis structure for nitrogen. The reason why they get one on each side before you double up is the electron configuration. Remember how we go up, up, up before we go back and go down, down, down? Remember that on your last test? So that the one on each side is showing the up, up, ups before you go down, down, down. So this is the electron configuration for nitrogen. Look at how it's got these two electrons are paired. This is it's called an unshared pair, and they do not make bonds. But nitrogen has 3 electrons right there ready to lose or ready to share. Nitrogen is a non-metal. It's far away from noble gases. It's 3 whole columns away. So it can lose all 3 of them, or it can work out sharing arrangements. It can do ionic or covalent. Okay, so that's going to help us with that. Now then, I got this little hands-on review break. Don't want to do it here. I think I want to do this first. Okay, so our cations are positive, the anions are negative. Then when you do when these elements get together and you're going to write their symbol or their name, you always do the cations first. So cations are first and anions are second. Okay, so we're going to do a little hands-on review break on how to put these together. And it's not going to be on the video because I'm going to be walking around the room. So I might make another video for the people who are out, because I have some people who will not be in class to learn this. So for right now, like, share, subscribe, and there will be at least one more part to this video, if not 2.